So target 5.3 in our unit 5 actually matches up with our section 5.3 in our textbook. So this is inverse functions, and the outcome is I will find the derivative of inverse functions. We're not going to integrate, we're just going to find the derivative and learn about the relationship between the derivative of the inverse function and the parent function or the original function. All right, so let's talk about inverse functions here first, just to refresh your memory. All right, so one simple function we just did, the ones we just did, is y equals ln of x and y equals e to the x. Those are inverse functions because they undo each other. All right, those are inverse functions. Here's another example of inverse functions. X plus 5, x minus 5. Those are functions that undo each other. All right. Let me talk about this one because it's easier to actually see when you're talking about this. So for instance, if I take this first equation and I put a 3 in there, I'm going to get the answer 8. So over here, I put an 8 in and I get the answer 3. Those are inverse functions because they undo each other. So if you start with x being 3 and add 5, you get 8. So to undo that process, you start with 8, you subtract 5, and you get 3 back. So inverse functions, if you remember from your algebra days, inverse functions, the domain and the range, spell this right, the domain and the range are swapped. All right, they're switched around. So here we have x, y. Over here, your x and y is the reverse of the ordered pair over here. Our x coordinate now becomes our y coordinate, and our y coordinate now becomes our x coordinate. So your domain and your range, remember domain is your input, which in this case is our x's. Your range is your output, which in this case is our y values. So our x's and y's are switched when you have inverse functions. So your ordered pairs are reversed. Now, the functions will undo each other. So another real simple functions that are inverses of each other is y equals x squared and y equals square root of x. All right, so we know if we put a 3 in here, we're going to get 9. And then over here, if we put a 9 in, you're going to get 3 back. So these are inverse operations because they undo each other. All right. So they are inverse functions, and your domain and your range are swapped. All right, so the things that we're going to have to know and do about inverse functions is these things over here are things we should know about an inverse function. Okay, so let's review a little bit. The vertical line test versus the horizontal line test. Okay, those determine if we have a function. So when you have if you have a function, say I have the function x squared. So let's just say I have the function y equals x squared. Then I know the picture looks like this for y equals x squared. If you do the vertical line test, which a vertical line test means you do vertical lines, and you only hit this function one time, then that means this is a function, a one-to-one function, right? Okay. The horizontal line test is where you do horizontal lines on the function, and that will tell you whether the inverse, which if you remember this is the notation for inverse, whether your inverse is a function or not. Okay, so since I do horizontals and I hit this parabola twice, that means my inverse is not a function. Okay, function means one-to-one, right? So in order for this to be for your inverse to be a function, we have to restrict our domain. So here's why an example down here, I have f of x equals x squared. I only have the right side of the graph. Okay, so if I only have the right side, then it passes both the vertical and the horizontal line test. Remember, the vertical line test tells whether the original function is a function or not, or what the original equation is a function or not. And then the horizontal line test tells whether the inverse is actually a function or not. Okay? Now, finding inverses. I'm going to remind you and teach you how to find an inverse. It's because your domain and range switch. To find an inverse, you're just going to switch your x's and your y's, and you're going to solve for y. So you're going to actually switch your domain and range and then solve. So that's pretty easy to find an inverse, and I'll show you that in some examples. A property about inverse functions, they are reflections of each other in the y equals x line. So if I take the y equals x line, which that's a diagonal line through the first and third quadrants, okay? So if I draw in y equals x on this picture here, so this is the line y equals x. It is the positive diagonal that cuts through the first and third quadrants. The function and its inverse are mirror images of each other, which means they're reflections across this line y equals x. So notice the green half of the parabola. If you mirror image it across, reflected across the pink line y equals x, you get the blue one. So that's a nice little property about inverse functions. When you graph those functions, they are mirror images across the line y equals x, the diagonal, the positive diagonal. And that's because your domain and range is switched. Here I've got the 0.42 and here I've got the 0.24. Those are mirror images across that line y equals x. Then we've got the last two here, which proves you have inverses. If you do the composition, you should get x. So when you put G into F, you should get x, or when you put F into G, you should get x. So we know the inverse function for x squared is the function y equals square root of x. We know those just like I have pictured here. So if I put this function into this one, then I'm going to have the square root of x squared, which gives me x. If I put this function into this one, then I have the square root of x quantity squared, which also gives me x. So if you substitute one function into the other, if you do both directions, putting g into f and putting f into g, if you get x as the answer, then they're inverse functions of each other. So those are all things you did in pre-cal, hopefully, when you talked about inverse functions. You did the vertical line test and the horizontal line test. You found inverses by switching your domain and range and solving for y. You learned that they were reflections of each other in the line y equals x. And that if you do the compositions, which you may have not seen it written this way, you may have seen it as written as F circle G and G circle F. So I call them fog and golf, but that's your circle composition functions. And so you did, I'm sure you did that in pre-cal at some point along the way. So in order for this graph here that I drew up here to be for its inverse to be a function, we can only have the right side of the parabola. So that's why there's only the green side for x squared. You don't have the left side. There's only the green side. So when you reflect that across this line y equals x, then this blue one is also a function. Okay? So the inverse is also a function, which of course is the square root of x. Now, what we're going to talk about today is the derivative of the inverse. Okay, so that's just about inverses in general. So what we want to talk about today is how do you find the derivative of the inverse? All right, so say we have function f being our x squared. Say that's our original function. So I want the derivative of g, which is the inverse. So I could write that as f inverse instead of giving it a new name g. And we know that's square root of x. What we want is the slope of the tangent line at what I call the mirror point. So we know the domain and ranges flip-flop between the function and its inverse. So here we have the 0.24 that's on x squared, and its mirror point is at the 0.42 on the graph of square root of x. So if you put a 4 in there, you get 2. But if you put a 2 into the function, you get the answer 4. So these are mirror points because they are mirror images, remember, across the line y equals x. Okay, so remember that across the line y equals x, inverses or mirror images. So I talk about these as being mirror points where you switch your x and y coordinates. So I have the point 2, 4 on F, and on my inverse, which I'm calling G, we have the point 4, 2. So what I want to know is what's the relationship between the slope of the tangent line at 2, 4 and the slope of the tangent line on the inverse at 4, 2. What is the relationship between these two slopes? Okay, that's what I want to know. So here's the theorem that tells us exactly down here. It tells us that G prime, which is our inverse, its derivative is the reciprocal of the derivative of the function. So if I did the derivative of x squared, if I find its derivative and then I do the reciprocal of that answer, that'll give me the slope for the other function, all right, for the inverse. Now, this looks kind of complicated because you wonder, why does it have this g of x here? Well, g of x is the y coordinate on my inverse, which means it's the x coordinate on the function. Remember, domain and range switch. So this is the y coordinate for my inverse, but it is the x coordinate for my function. So what you do is you find the derivative of the function at its x coordinate, and then you do its reciprocal. And the reciprocal of that slope is the derivative of the inverse at the mirror point, okay, at the mirror image. So let's just try that real quick here. All right, so here I've got f equals x squared, okay, so f of x is x squared. So my derivative of that is going to be 2x. And I'm looking at the point 2, 4. So f prime of 2 is going to give me 2 times 2 is a slope of 4. All right, now let me do the inverse function, which we know the inverse function, g of x, which I could call f inverse if I wanted to. All right, they'll use different notations. They'll sometimes call it a new function g, or they may just use, say, f inverse with a little -1. So that's square root x. So I want his derivative. Well, that's x to the 1/2. So g prime, which is actually f inverse prime. Whoops, my pen. All right, f inverse prime of x. So I'm going to multiply the 1/2 to the front, and then I'm going to subtract 1, gives me -1/2. So that's a square root in the denominator. So I get 1/2 square root of x. So that's my derivative. So now I want the value of the tangent line, the slope of the tangent line at the point 4, 2. So I'm going to do g prime of 4, which is f inverse derivative at 4. Okay? So I'm going to put a 4 in here. So 1/2 square root of 4. Which square root of 4 is 2. 2 times 2 is 4, so that's 1/4. Notice that your slopes are reciprocals of each other. So the slope of the tangent line on x squared at the point 2, 4, that has a slope of 4. The slope of the tangent line on the inverse, square root of x, at the point 4, 2, it has a slope of 1/4. So this has a slope of 4. This has a slope of 1/4. So the tangent lines on inverse functions at mirror points have slopes that are reciprocals of each other. And that's really all you need to know about inverse functions for the calculus exam, for calculus. You just need to know that the relationship between the slope of the tangent lines at mirror points on the function and its inverse, those tangent lines have slopes that are just reciprocals of each other, just flipped upside down. That's all it is, right? So that's your content video, and so next you need to watch your example video.